Montague.
I'm Derrick Chun.
I'm Marianna Sbordone.
I'm Meyer.
And today we're going to be giving you a quick crash course on the use of gold nanotubes for cancer treatment. As we just mentioned, gold can be used to treat cancer patients and their tumors and destroy cancer cells. And we're going to be talking about the structure of the nanoparticles and the effects those properties have on the gold particles themselves. As you know from class, anything in red is stuff you don't know, and we will hopefully be teaching you by the end of this course, or in this case, the next 15 minutes. The types of cancer treatments, this type of cancer treatment needs future improvements before it can be widely used, and hence the research. It's an active area of research, and it's almost primarily in mice and small rodents. So the development of new approaches to detecting and treating cancer has led to a rising in the healthcare costs in the United States and across the world. So the purpose behind this research is to A, treat cancer better, and B, bring this cost down such that individuals without the access to resources like some the American populace can actually get treatments for their cancer. Improving the efficiency of the method of delivery is an important process. Cancer is a terrible disease, and cancer treatment is really not much better. Chemotherapy destroys basically all the working parts of the human body, and radiation treatment is almost as bad. And so the ability to treat cancer without invading the self in that same way is really important, and will help improve the quality of life and reduce the side effects of cancer.
Now we will go over the exact process by which cancer is treated using these gold nanoparticles. First thing that the doctors will do is they will introduce the nanoparticles into the bloodstream, and this little diagram here shows how the process of endocytosis and how these nanoparticles get into the cancer cells. Go ahead. After the nanoparticles are introduced into the bloodstream, they will bind to the tumor. This image here shows the nanoparticles bind to the tumor itself. This process is done by taking advantage of how tumor cells change the properties of the blood vessels. That a blood vessel in a tumor cell will be more permeable, so the gold nanoparticles will get through the blood vessels and get into the tumor. One problem this gives, though, is that it depends on a late-stage tumor, where an early-stage tumor will have less permeable blood vessels. After the nanoparticles will get onto the cancer cells, it will be exposed to an excitation source. In the clinical trial we found it was near-infrared light, and taking advantage of the properties of the nanoparticles, the nanoparticles will absorb the light and release heat, which will kill off the cancer cells without harming the intact healthy cells, thereby killing the cancer. This is the result of a clinical trial in mice in the lab. This graph here shows the growth of the tumor over time. This graph here shows a control where it was a phosphate buffering solution was introduced to the tumor. This one here shows a direct introduction of the nanoparticles into the tumor itself. There is a significant reduction in the growth of the tumor as compared to control. However, the scientists found an issue of whether or not it was clinically applicable to introduce the nanoshells into the tumor itself in an actual patient, so they decided to introduce the nanoshells into another site farther away. This particular trial they introduced into the tail. While there was also significant drop in tumor growth, there was also an issue of whether or not enough nanoparticles were getting to the tumor itself to significantly kill the cancer cells.
So now we're going to discuss the nanoparticle properties, specifically for our gold nanoparticles. The first feature of note is the surface plasmon resonance of these particles. This is a property that's intrinsic to metal nanoparticles, and it basically involves the ability of the particles to be excited by oscillations caused by light. The next property is the ability to bind to amine and thiol groups, which is important for biocompatibility. The next property, as previously mentioned by Derrick, is enhanced permeability and retention, EPR. This diagram here shows that process in more detail. As you can see, the nanoparticles can't pass through healthy tissue because they're too large in size. However, when the nanoparticles travel to areas in the blood vessels which is surrounded by tumor tissue, there are gaps in these leaky blood vessels where the nanoparticles can pass completely through and attach to the tumor. Another important property of these gold nanoparticles is the ability to resonate when they are exposed to specific frequencies of infrared light. This is what enables the particles to transform this light energy into heat and melt the cancer cells. As previously mentioned, they are biocompatible. However, some of the preparations, which we'll go into next, have shown to be toxic in vivo and in vitro. So more research needs to be done in these areas to ensure that the patients are not further harmed by these processes. And finally, they're able to bind to targeting agents, which is important for other applications aside for cancer research. And they are small in size and high in atomic number, which allows easier absorption of UV rays. To give a brief overview on the processes that we'll talk about next, all of these synthesis processes are actually performed in liquid, so they're categorized as liquid chemical methods. The simplest of these methods is the Derrick method, and it basically just involves the reduction of hydrochloric acid in water, and using a reducing agent that contains some form of silver. A variety of reducing agents are used. And this process will produce nanoparticles that are 10 to 20 nanometers in size. The process which it goes through is shown in this diagram here. Basically, the particles are reduced and reoxidized and go through a nucleation phase. I thought this was really interesting because we talked about nucleation and growth in class, and here is a real-life example of one that's used in experimental and real-world scenarios. So once the gold atoms are reduced from Au3+ to Au, basically the solution of water and this gold-containing compound will become supersaturated, and the particles will precipitate out on that size scale that I mentioned previously. The next most widely used method is the Brust method. Similar to the Derrick method, except for this method takes advantage of organic liquids, which can sometimes be more easily used in clinical applications. This process is shown here in this diagram. Apologies if it's a little difficult to read. But basically we start off with the same chloric acid, but in this case it's mixed with, excuse my pronunciation, tetraoctalamonium, which is a reduction agent in this case. It's stirred continuously for 2 hours and mixed with toluene and sodium bromohydrate, which act as a reducing agent and an anticoagulation agent, respectively. These are both important because it would be non-advantageous if the nanoparticles clump together before they're able to be injected into the patient. To give a brief overview of some of the less widely used methods that exist, there's a sonochemical method where the solution is agitated using a standing wave. There's the template method where nanoparticles are actually formed in a very small membrane of aluminum. And this method is how we get different shapes like nanotubes rather than nanospheres. Also green chemistry, which is actually just being researched currently, which involves using cyanobacteria to reduce Au3+ to Au. And finally, there's also the photochemical approach, which uses UV radiation to speed up the process.
So as Marianna was talking about, there are different shapes of gold nanoparticles. So the main two we're going to focus on are seen here, gold nanospheres and gold nanorods. However, there are 2 other types known as gold nanostars and gold nanotriangles, but these are the main 2 being used in this type of cancer treatment so far. So we're going to start with gold nanoparticles. So those were developed in 2003, and they're also known as gold nanoshells. So the way they're composed is they have a silica core with a thin gold overlay. And on top of this overlay, we add some seeds of gold colloid, and these are just there to add more gold and complete the shell. So we kind of have a picture of how this looks over here. So we have the center of the nanoparticle as well as a protective layer followed by a soluble biocompatible layer, which is used for the in vivo delivery. So these particles are special because they can convert light into heat, which is used to kill cancer cells. And this was demonstrated in tumors in both mice and dogs. And they can also function as imaging probes in dark field and 2-photon microscopy because they add contrast to the microscopy itself. However, they are of a large size, larger than nanorods, and this is good for the scatter-based imaging because they add that contrast, but it's not as good for in vivo delivery. Then we have gold nanotubes. So gold nanotubes are also called gold nanorods. They're generally smaller than gold nanoshells, and they have higher absorption coefficients as well as narrow spectral bandwidth. So you can break down their absorption peaks into two, which is longitudinal resonance and transverse resonance. So to compare these two, we have nanoparticles and nanorods. They both have a size and shape that impairs effective in vivo delivery. However, nanoparticles have larger photothermal transduction cross-section, which I think means that you can disperse the heat better throughout the tumor. Nanorods, on the other hand, have superior absorption cross-section, so they can absorb more light to turn into heat, but they're susceptible to becoming gold nanospheres when they're given too much intense laser illumination.
So there are challenges to overcome. While using gold nanoparticles in cancer treatment is an amazing new discovery, it does have a long ways to go. There are issues with the penetration depth of the near-infrared radiation into the human body. Other frequencies have been attempted, but X-rays and etc. Do have the impact of negative problems in human cells, generating more cancer, which is not really the goal of cancer treatment. So maximizing the amount of actual nanoparticles that bind to a tumor is a problem, as was mentioned before. The current method is just injecting them into the body and letting them accumulate around tumors naturally. And methods of introducing biological agents into the design of the particles will help with this. Producing anything with gold is going to be expensive, and it's also difficult to work on a scale that's on the nanoscale. And so economically producing these particles is something that's being researched and needs to be fixed. And the ability of the particles to bind to the tumor through bloodstreams depends on tumor development. So finding a way to tailor the size to the tumor and having a wide variety of particle sizes so that you can treat small and large tumors efficiently is going to be a method. And then there are questions about the long-term side effects. There have been issues with toxicity in some of the structures, especially bioaccumulation in the body can be a major issue. And so the future of gold nanoparticles is very promising. Better nanoparticle accumulation on the tumor is being developed, especially through the design of the actual particle and introduction of the biological agents, as was mentioned, especially receptors and antibodies that will potentially bind to tumors and tumors alone. And then adding to that, the improvement of early stage treatment with the dark field imaging and actually targeting very small cells before they're visible in any real way is useful. And then tuning the structure to maximize the response, safety, and effectiveness is ideal, and that is a long-term solution to this problem, and that is, once it works and being able to use it clinically, finding the ideal golden zone where these work perfectly is going to be a problem, but the future of gold nanorods. So that brings us full circle, and as we've mentioned, gold can be used to safely destroy cancer cells in living patients, and ideally, eventually, living human beings. The structure of the nanoparticles was explained at the beginning of this, as well as the properties and how the particles are produced. And this type of treatment does need future improvement before it can see any sort of human trial or wide use at all. But the world is promising, and moving forward, you can clearly see how material engineering is going to be useful not only in design of large-scale structures, but actually in the medical world too.